Hello, my name is Peter Tucker. This is my oral report on nanotechnology of carbon nanotube use and energy storage. I'm going to provide a brief introduction into carbon nanotubes, what they are, and where they come from. Improvements in energy storage of batteries and supercapacitors using carbon nanotubes, and then a conclusion, and then a reference page. Here's the introduction. Carbon nanotubes are developed from the synthesis of graphene, which is one type of molecular compound of carbon. The carbon atoms are in a hexagonal lattice chain sheet, one atom thick. The entire length of the molecule is as long as the sheet itself. Graphene is the most chemically reactive form of carbon due to the large lateral surface. Graphene was first created by pulling the layers of graphite apart using tape. It is now being created using an industrial blender and a little soap and water mixed with the graphene, or mixed with graphite. Carbon nanotubes resemble rolled up graphene sheets, either in single wall nanotubes or multiple wall nanotubes. Carbon nanotubes are created in a temperature-controlled heating chamber process, where vaporized hydrocarbons stack between a catalyst and a substrate surface, building a lattice directly underneath the catalyst. The angle of the lattice affects the conductivity from metallic to semiconductive. These conductive metallic properties that carbon nanotubes can exhibit are from the mobility of electrons through the material, called transference. The formation of carbon lattice angle has been shown that it can be controlled using temperature and pressure within the chamber, which provides a large variety of implementations within electrical manufacturing. Improvements in batteries and supercapacitors. Research on carbon nanotubes doped with nitrogen or boron atoms incorporated into lithium-ion batteries have provided more areas for lithium ions to be stored and for easier diffusion through the system. This greatly improves lithium-ion batteries by increasing energy storage capacity and providing more recharge cycles throughout its lifetime. Growing carbon nanotubes on electroplates, researchers at MIT found they could greatly enhance the regular capabilities of supercapacitors. Like use in battery technology, carbon nanotubes with bonded nitrogen or boron atoms increased electron storage collection and transference by many magnitudes. MIT researchers even founded a company called FastCap Systems to start developing these technologies for use in industry. Since there are no redox reactions with capacitors, electron transference to and from the capacitor is rapid and highly powerful. But this also means that there's generally less energy available compared to a battery of the same size. The advantage of supercapacitors is their theoretically infinite recharge cycles at very quick rates. Further advancement of supercapacitors was presented by Rice University, who grew carbon nanotubes on top of a sheet of graphene, creating even more conductivity for electrons, while reducing the cost of production. In 2014, FastCap Systems started to put out their supercapacitor products into the market. Their supercapacitors were used in drilling equipment and offered more resilience to temperature and pressure while providing a stronger signal from the available energy than batteries that were used previously in these operations. They have been developing supercapacitors for NASA in missions that require extreme temperatures from both ends of the spectrum, by wanting to go into deep space and also missions to Venus. Their advanced supercapacitors are able to store 10 times the amount of energy and power density as commercial competitors. These improvements in supercapacitors would be of great benefit implemented in cell phones, electric and hybrid automobiles, and in renewable and alternative energy resources, where the biggest obstacles to overcome are those of efficient energy storage and discharge. There are still improvements in energy storage that need to happen to make them more commercially viable, including scalability for more practical uses. Developments in 2015 from UCLA's California Nanosystems Institute built hybrid supercapacitors using laser-scribed graphene and manganese dioxide to hold large amounts of charge. This technology could possibly be fused with nanotube supercapacitor technologies to provide a more reliable and low-cost supercapacitor. Research done by the University of Adelaide in Australia shows wasted plastic bags can be reused as a carbon resource and can create carbon nanotubes using a low-impact production process. By cutting up the plastic bags into squares and weak acid etching, they created a waste-free synthesis of carbon nanotubes that were in turn used to produce filters for desalinating water. This kind of ingenuity shows a wealth of practices to turn non-degradable waste into reusable materials for environmental cleanup. The increasingly low costs of building carbon nanotube supercapacitors, added with their high energy output, limitless recharging capabilities, when developed with low environmental impact practices and from plastic bag waste, proves to be highly beneficial in providing large volume, high strength energy while helping to clean up our environment. In a world of finite resources, fossil fuels are running out, and other natural resources are becoming scarce. Emerging carbon nanotube technology has the potential to provide a non-toxic, energy-efficient means of storing and transferring renewable energy, like photovoltaic solar, wind, geothermal, among other developing energy technologies, to help us live closer within our means of ecological permanence. And here is a list of references. Thank you very much.